Alright, so here we have a vector decomposition problem in which I have this vector f, and when I split it into pieces in the e hat 1 direction and e hat 2 direction that are defined as indicated in this figure. Now if you follow my recipe, and I encourage you to do so, what we do is we create this vector triangle where f itself is the hypotenuse of the right triangle. It's a right triangle because that angle right there is 90 degrees. And the other two sides of the triangle are carefully chosen so that these two vectors add up to the f. So they're arranged in this tip-to-tail fashion right here. And these other two sides aren't just arbitrary vectors. What they are vectors that are parallel to the e hat 1 and e hat 2 vectors, or basis vectors. So this piece right here, that one right there, that's parallel to the e hat 2 direction. And this piece right here is parallel to the e hat 1 direction. Again, they're in tip-to-tail fashion so that these two vectors add up to f. And now what we need to do is find the lengths of these two sides in comparison to f so that they add up properly. And what we have to do is we have to define an angle, right? So an angle is given to us, this thing called theta, and it's the angle of this sort of slope line right here relative to the vertical. So it's this angle right here in our triangle if we were to define it, right? But that's kind of hard to work with that angle right there. But notice that the f is horizontal, this thing was vertical right there. So if this angle is theta, then this angle inside right there, that has to be 90 degrees minus theta. And you remember, for a triangle, all the angles of a triangle have to add up to 180 degrees. So let me just call this thing alpha right there. And if this is 90 degrees, then I got alpha, and I'll call this one beta right there. So I've got alpha plus beta plus 90 degrees. That has to add up to 180, which means alpha plus beta have to add up to 90 degrees. So these two angles have to add up to 90 degrees, that one and that one. So, look at that. So if this angle right here is 90 degrees minus theta, then this angle right here has to be theta. So now I've defined my signs in terms of the angle that's given to me. So this explains why, in my vector decomposition, my answer right here, the e hat 1 component, which one's the e hat 1 component? It's the one that's sort of sloped that way. So here's the e hat 1 component. It's opposite of that angle theta, so that's why I have an f times sine theta right there in the e hat 1 direction. Whereas this piece in the e hat 2 direction, that's adjacent to the angle of this right triangle, adjacent to the angle theta, so that's why I have an f times cosine there. Now, of course, it's also important to get the signs exactly right, too. So notice that, let's look at the e hat 1 direction. So this e hat 1 component of the f, that's going up and to the left, whereas the actual e hat 1 basis vector is down and to the right. So this thing's actually in the minus e hat 1 direction, which is why I put that minus sign right there. And likewise, this e hat 2 component, it's actually in the opposite direction of the e hat 2 vector. So that's why there's a minus sign right there as well. So for my answer, I get this expression right here, which is so good. I'll put a box around it. Right? It's also worth noting that when I drew my forced triangle, I went in the e hat 2 direction first and then the e hat 1 direction second. It doesn't have to be that way. I can go in the e hat 1 direction first. Like, in other words, I could have gone this way first, right, in the minus e hat 1 direction, then this way in the minus e hat 2 direction. And if you do that, you'll find out you get the exact same thing. In fact, you'll find that since this angle right there was theta, you'll find that that angle right there is theta. And you'll find out the trigonometry works exactly the same. Go ahead and try it yourself if you want it to go this way. All right, so we're done. Over and out.